Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 36, in which I will solve some problems of Fermat's little theorem. Now we solve a problem. Problem is prove that 8th power of any integer is of the form 17n or 17n plus minus 1. Now we solve this. Let a be any integer. Then 17 may divide a or 17 may not divide a. If 17 divides a, implies that a equal to 17k, k is an integer. Implies that a to the power 8 equal to 17k to the power 8. Implies that a to the power 8 equal to 17 multiply 17 to the power 7 multiply k to the power 8. Implies that a to the power 8 equal to 17, let this is equal to n. Let 17 to the power 7 multiply k to the power 8 equal to n. This is equal to 17n. Here n is an integer. Let this is number 1. Now we deal the case when 17 does not divide a. Since 17 is a prime number, therefore, by Fermat's little theorem, a to the power 17 minus 1 is congruent to 1 modulo 17. Implies that a to the power 16 is congruent to 1 modulo 17. Implies that 17 divides a to the power 8 square minus 1 square. Implies that 17 divides a to the power 8 plus 1 multiply a to the power 8 minus 1. Implies that 17 divides a to the power 8 plus 1 or 17 divides a to the power 8 minus 1. Implies that a to the power 8 plus 1 equal to 17k1 or a to the power 8 minus 1 equal to 17k2. k1 and k2 are integers. Implies that a to the power 8 equal to 17k1 minus 1 or a to the power 8 equal to 17k2 plus 1. This is number 2 and this is number 3. From 1, 2 and 3 we get that a to the power 8 is of the form 17n or 17n plus minus 1. N is an integer. Proved. Now we solve the next problem. Problem is if 7 does not divide a, prove that either a cube plus 1 or a cube minus 1 is divisible by 7. Now we solve this. Given that seven does not divide a, here a is an integer. Since 7 is a prime number, therefore by Fermat's little theorem, a to the power 7 minus 1 is congruent to 1 modulo 7, implies that a to the power 6 is congruent to 1 modulo 7, implies that 7 divides a to the power 6 minus 1, implies that 7 divides a cube whole square minus 1 square, implies that 7 divides a cube plus 1 multiply a cube minus 1, implies that 7 divides a cube plus 1 or 7 divides a cube minus 1. Proved. Now we solve the next problem. Next problem is if P is an odd prime, then using Fermat's little theorem, so that number 1 to the power p minus 1 plus 2 to the power p minus 1 plus p minus 1 to the power p minus 1 is congruent to minus 1 modulo p. Number 2, 1 to the power p plus 2 to the power p plus plus p minus 1 to the power p is congruent to 0 modulo p. Now we solve this. Since given that P is an odd prime, therefore P minus 1 is an even number. Since 1, 2, 3 p minus 1 are integers, less than p, and P does not divide 1, P does not divide 2, P does not divide 3, dot 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 dot, P does not divide P minus 1. Therefore, by Fermat's little theorem, one to the power P minus 1 is congruent to 1 modulo P. 2 to the power P minus 1 congruent to 1 modulo P. Dot 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 dot. P minus 1 to the power P minus 1 is congruent to 1 modulo P. Let this is number 1. Adding all these, we get 1 to the power P minus 1 plus 2 to the power P minus 1 plus dot 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 plus P minus 1 to the power P minus 1 is congruent to 1 plus 1 plus 2 to P minus 1 terms modulo P, implies that 1 to the power P minus 1 plus 2 to the power P minus 1 plus dot 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 plus P minus 1 to the power P minus 1 is congruent to P minus 1. 1 plus 1 plus 1 to P minus 1 terms is P minus 1 modulo P. Since P minus 1 is 1 less than P, therefore we may write this 1 to the power P minus 1 plus 2 to the power P minus 1 plus dot 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 P minus 1 to the power P minus 1 is congruent to minus 1 modulo P. Number 1 proved. This is number 2. Now we solve the number 2. Multiplying congruences of 1 by 1, 2, dot 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 P minus 1 respectively. We get 1 to the power P. 1 multiply 1 to the power P minus 1 is 1 to the power P is congruent to right side 1 multiply 1 is 1 modulo P. Here if we multiply 2 in both sides, 2 multiply 2 to the power P minus 1 is 2 to the power P, and in right side 2 modulo P dot 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 dot. Now if we multiply this by p minus 1, we get p minus 1 to the power p, congruent p minus 1 modulo p. Let this is number 3. Adding all these, we get 1 to the power p plus 2 to the power p plus dot 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 plus p minus 1 to the power p is congruent to 1 plus 2 plus dot 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 plus p minus 1 modulo p. Let this is number 4. Implies that 1 to the power p plus 2 to the power p plus p minus 1 to the power p is congruent to p multiply p minus 1 by 2 modulo p. Let this is number 5. Since p is an odd prime, therefore p minus 1 is an even integer. Let p minus 1 equal to 2 multiply k. K is an integer. This is the formula for denoting an even integer. Therefore, p multiply p minus 1 by 2 equal to p multiply p minus 1 is 2k by 2 equal to pk. Let this is number 6. Since p divides pk, implies that p divides pk means p multiply p minus 1 by 2, implies that p divides p multiply p minus 1 by 2 minus 0, implies that p multiply p minus 1 by 2 is congruent to 0 modulo p. Let this is number 7. From 5 and 7 we get 1 to the power p plus 2 to the power p plus dot 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 p minus 1 to the power p is congruent to 0 modulo p. Since here in right side we see that p multiply p minus 1 by 2, here in left side we see the same number. So we get this result, therefore proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.